In the lab, you'll be working with one of these little ADXL 335 accelerometers. It's mounted on this plastic element so that you could put it flat, flush onto the table on that side. Now, it's got three axes, X, Y, and Z, and by aligning it flat on the table, you'll have the X-axis hopefully horizontally. So all you'll see are accelerations as it moves back and forth in the X direction. Now to calibrate it, you can set it down flat on the table. That should give us 0G in the X direction. Then we can tip it up on one side. That's plus 1G and minus 1G. So that should give you all the information you need in order to come up with a calibration so that you've got this accelerometer calibrated. Here's some accelerometer data on the serial plotter, and right now it's just sitting on the bench. But if I touch it with my fingers, well, I get an initial transient, and it seems to be shifting around a little bit relative to 0 as I rock it back and forth. So getting an accurate 0 value right on the horizontal is going to be difficult. But now as I move it back and forth on the desktop, we can see that the accelerometer is experiencing some acceleration, and that looks like it might be noise. But I'm also hearing some noise. I'm rubbing it back and forth on a rough surface, so maybe that's the actual acceleration that it's experiencing. So I'm going to pick it up off the table now, and I'll move it back and forth in the air where it's not subject to that friction. And that seems to be a much smoother acceleration until the cable gets caught on something. So I think this is a real acceleration with real changes, rapid changes in the acceleration it's experiencing as it runs over a rough surface. Now I'll stop again. Moving the accelerometer back and forth on the table like this has some friction effects, which leads to spikes in the acceleration data. If I lift it up just a little bit and move it back and forth like this, then those spikes go away. So I'm measuring some real data there, real roughness in that acceleration time series, and I'll need to integrate that to get velocity. So now I'm going to switch on the velocity trace. Back and forth, something like that. That's giving accelerations of about 3G. We should be able to integrate that in order to get the velocity as a function of time, and possibly even the position as a function of time. So I've recompiled the code, and now the red is velocity. And we can see it's showing a sinusoidal oscillation that goes along with the sinusoidal oscillation of the acceleration. But it's also got a continuous rise to it, reflecting the fact that there is a positive value to the acceleration. So this drift is coming from the lack of the correct 0 on our acceleration. On average, the acceleration is adding up to positive, and that clearly can't be quite correct. You will need to figure out in the lab how to minimize that drift, and that's going to be one of the big targets this week.